Well, ladies and gentlemen, good afternoon, and thank you for coming so numerous to this presentation, where my colleague Olivier and myself, we are both a research engineer at Consensus, we are going to present you the technical underpinnings of the Linea zk rollup level 2. And yeah, we'll try to answer all of the questions that you may have on this subject. So here is a basic plan of the presentation. So first we will tell you what is Linea. Then we will detail the three main technical components of Linea, so the arithmetization, the state management, and the prover. And finally, we will give you some info regarding the release and the coming roadmap of the Linea product by Consensus. So let us start with what is Linea. Linea is a level 2 zk rollup. So what is a level 2 zk rollup? Let us unwrap that a little bit. So a rollup is a way to optimize and to scale up the Ethereum blockchain. So the idea is that we are going to switch from a monolithic architecture where the execution of the transactions, the settlement of the transactions, the state, and so on are all handled in a single place, to a more modular architecture where you have a first block that is the execution block, or what we call level 2, where you are actually going to execute the transactions. And you will be able to do that faster than on the Ethereum mainnet. And then the proof of the correct execution of this level 2 chain will be published and verified and validated, leveraging the L1, so the Ethereum mainnet, and the consensus mechanisms that you can find on it. So this is a global idea of a rollup. There are several ways of doing rollup, and Linea is a zk rollup, or sometimes also called a validity rollup. So how does this work? Basically, a zk rollup is a huge state function, transfer function, that is going from a state I of the L2. You inject into it a lot of transactions, so a block, and then you get a state I plus 1 on the L2. Now, how do you prove that you didn't cheat on the execution of this transaction, or that you didn't give too much or not enough money to the people involved? You have here this big function, the zkevm, that will be generating a lot of data that will then be used by a prover to testify and to ensure that you didn't cheat on the execution of all these transactions and that you were truthful in your implementation of the Ethereum protocol. And then this proof, which is let's say in size in bytes, rather small and very hard to compute, but very easy to verify, will be published on the L1, so on the Ethereum, in the call data of a transaction from the zk rollup operator to the L1 smart contract of the rollup. And this way, we'll be able to fit in a single transaction on the L2 a whole block or even several blocks of the L2. So there are many ways and many different complexity for implementing zk rollup. There is this classification that has been established by Vitalik a few years ago that is more or less accepted in the ecosystem. And for now, Linea is a type 3 zk rollup, which means that we are bytecode compatible and language compatible with Ethereum mainnet, but we are aiming in the coming months to go to the type 2, which means that we will have proved the integrity of the Ethereum API, and that we will have a very similar gas calculation when it comes down to the differences between the L2 and the L1. So why should you use Linea? It depends. If you are a user, you would like to use Linea because everything is cheaper. All of the transactions tend to be cheaper. You get more transactions in the same slice of time, so you have higher transactions per second, which leads to less congestion of the network. If you are a developer, you would like to use Linea for a few reasons. The first one is that you can use Linea exactly as if you were using the mainnet, thanks to our goal of 100% compatibility between the L1 and the L2, and which leads to the fact that you can seamlessly reuse all your existing code, either at the language level like Solidity or Viper or whatever you like, or at the bytecode level. And finally, you will be able to address all of these users and create a mutual emulation of people wanting cheaper and faster transactions. And on top of that, of course, you will get integration with the whole consensus ecosystem, so MetaMask, Infura, Truffle, and so on and so on. So what are the challenges on our side of developing and implementing such as zkevm? So first thing first, the EVM, so the Ethereum virtual machine, is composed of many parts related either to the state or to the precompiles and so on, that are strongly coupled and that are quite interdependent, which is sometimes hard to modelize in a cryptographically provable way. Second, there are many data in the EVM that are making it very hard to actually arithmetize or to express in terms of AAR constraints. The auditability is another key point. You need to be trusted, to be truthful for your community. So you have to get an auditability and to get audits for all of your software pieces. And finally, the performances, especially the creation of the proof, is something that is computationally very expensive, and still you have to do it quickly so that it is done in the time of the generation of a block, and quite cheaply in terms of gas, so that you do not pay too much gas on CL1. So to see how we addressed all of these points, I will now give the mic to Olivier that will be presenting you the main technical points of Linea.
Thank you, Franklin. All right, so I'll try to give a bit of an insight into several of the components, not all of the components, that go into Linea on the EVM side and the arithmetization and prover side. So I'll be talking about the arithmetization itself, the way we represent the state, and also the prover. So let's start at the beginning. So the arithmetization is really comprised of two essentially independent components. The first one are the constraints. So this is the logical heart of the arithmetization. Constraints are just equations. And to produce an arithmetization of the EVM is to produce a collection of these equations, a collection of such constraints, which should have the property that when one is able to satisfy all of these constraints simultaneously, it should be basically equivalent to having executed a collection of transactions, a block of transactions, basically. Okay, and what does it mean to handle these transactions? Well, we want to be able to do the entire life cycle of a transaction or of a batch of transactions, starting with the transaction itself, which is presented to us in the standard RLPized format in which it is also used in mainnet. Decoding this, extracting the fields, executing the EVM bytecode if necessary, if it is a call to a smart contract, let's say, and finally finishing with producing the transaction receipt, which is associated to the transaction. And all of this, of course, for a block of transactions. But this is not all, because the EVM is not just a virtual machine that runs in the ether. It is connected to a state. So the arithmetization also comprises this part, which is we need to connect, be able to read and update, that is, we need to connect with the L2 state. And this too must be part of the arithmetization. And finally, there are certain cryptographic operations that sort of live in a world of their own, a class of their own, which are ubiquitous throughout the EVM, be it hashing, such as SHA-3, SHA-2, etc., or precompiles. And this is a whole different part of the arithmetization, which I will not be talking very much about today. Okay, I said the arithmetization is a collection of constraints, so of these equations written as equalities between various variables in some sense. So the link I posted here is a link to the spec, which we published recently, and which purports to be a full spec for the EVM. So all of the opcodes are handled and all of the sort of strange behavior of the EVM itself. But the other part of the arithmetization is trace production, because these constraints, these equalities, they apply to something, and that something are traces. Traces are these very large matrices which are compiled as an execution client, in our case Besu, is running on these transactions. And as I said, they are the recipient of the constraints. Constraints apply to these traces. And yes. So just to give you an idea, so just imagine you have these extremely large matrices with, in some case, maybe 100 columns or maybe more, and that are extremely deep, on the order of millions of rows, and they are subject to these hundreds, if not thousands, of constraints which are compiled in the specification. So the EVM is a very complex piece of software, or of it's a complex architecture, and we are sort of forced in our arithmetization to break apart the complexity. And thus the arithmetization is really comprised of many different chapters which each represent a sort of a semi-autonomous and semi-independent little box which sort of corrals a certain collection or certain section of the complexity. And these boxes, though they are somewhat independent, they are actually connected to one another, as represented in this diagram by these arrows, which are these cryptographic arguments to sort of transfer data, these lookup arguments. And another part, which I didn't depict here, is the offloading of certain parts of the arithmetization, such as computing precompiles, etc. So how does one go about, now that we've broken up the complexity into little chunks, how does one go about actually writing a part of the arithmetization, a module, as it were? We are thankfully in a position where we can sort of almost forget about the fact that we are handling cryptography in the background. So several at least, some of the sort of standard tools one would expect when writing a program are actually available to us in this sort of pseudo language, or sort of, not pseudo language, but more like high level language. We can seamlessly do conditional branching. We have a sort of a primitive type system. We can do function calls, and we can do sort of internal consistency arguments, which basically mimic memory for certain parts of the EVM that may impact the execution at various points in time. You can think of storage, you can think of RAM itself, you can think of warmth of addresses or warmth of storage keys, etc. And the main point I want to make is that when writing such a module, we are in some sense writing something which is removed from cryptography. Everything we want to do has a cryptographic equivalent on the right-hand side. And concretely, we use this Lisp-like language which allows us to succinctly write these constraints in this proof format that we use, which is this algebraic intermediate representation. And there is a very tight connection between the spec itself and what is actually written in this Lisp, in these constraints files. And then this is also used as the sort of input to produce the actual constraints, the sort of compiled constraints that we don't want to have to deal with on our end, directly at least. Okay, let me say a few words on the state manager. So as Franklin said, we are not a type 1 zkevm. We don't abide by the same representation of the state. And concretely, we have two major differences. In the state itself, we substitute catch-arc, which is sort of very difficult to arithmetize, with something which is much easier to arithmetize and for which we've already done previous work. We use the MIMC hash function family, for which we have extremely efficient proving schemes. The other major difference is that we don't represent the state as a Patricia Merkle tree, but rather as a sparse Merkle tree. And the state manager is a component that basically handles the sparse Merkle tree side of things. And it provides the arithmetization, so the zkevm, with all the data it needs, such as nonces, balances, etc., etc. And it provides the prover with the justification for these data, such as Merkle proofs, Merkle paths. So concretely, though, there is still a Patricia Merkle tree in the background. So as I said earlier, we're using Besu as our execution client, and Besu uses the standard catch-arc-based Patricia Merkle tree. We have a plugin, I didn't change the slide, but based on Bonsai, we have a plugin that converts or sort of produces these trilogs that are then passed on to the state manager. So all the accesses that are made to the state, all the changes potentially that are made to the state are then passed on to the state manager, which produces the data which will later on be required by the prover, such as all these Merkle paths I was talking about. The advantage being that this representation allows us to easily integrate into the prover itself in the end. Another advantage of this is that if need be, in the future, we could also replace MIMC with a different hash function if we find something that is more efficient maybe and doesn't compromise security. Okay, let me quickly finish on the prover. So it's kind of strange to do a very short part on the prover because the prover is an extremely complex piece of the entirety of Linea. Because the prover is tasked with sort of reconciling everything. So I presented these two main boxes up to now, which is the zkevm itself, which is the sort of execution logic of the EVM. I talked a bit about the state and accessing data and updating data. But I mentioned it a few times, there's also the crypto side of things, so all those cryptographic primitives that are really nasty to arithmetize. The prover, all of these comprise the arithmetization as well as the connections between them. And the goal of the prover is to produce these succinct cryptographic proofs that testify to the validity of these boxes individually as well as the connections between them. There are issues though. When we run the zkevm, we very quickly produce traces that are absolutely humongous in size. So the number of cells n will be on the order of billions, right? Billions. Yeah, so on the order of billions. So it's extremely large, and it will not fit into any L1 compatible proof, at least naively. Furthermore, the prover sort of mixes, or at least what is given to the prover, is a mixture of all kinds of different constraints. We have permutation arguments, we have evaluations, we have global evaluations, local evaluations, we have lookalike arguments, we have range proofs, etc. So the solution that we have, which is this vortex proving system, is to sort of first do a first compilation step, where all of these disparate kind of constraints are converted into a single kind of constraint, single kind of evaluation constraint. This is the step we call arcane. It's a sort of reduction step. It usually blows up the size, but at least it produces uniformity in another sense. And we then have the second step, which is a compression step. This is where vortex enters the picture, which is sort of simultaneously a scheme for compression, but also a hash function. And the argument is basically reduced to an argument that is of square root of its original size. And this process can be done many times over. The reason being that verifying this compressed proof is itself doable in a circuit. So we can sort of have this self-recursion mechanism where we have this feedback loop where we can do this step many times over. Sorry. Okay, and we basically continue doing so. So we can't do it infinitely often. At some point, the benefits die out. But we do it until a point where the proof becomes manageable in size in the sense that we can produce a proof which is L1 compatible, so we can produce a Plonkish style proof for the entirety of the argument. And at this point, we are able to publish it on mainnet and to have the smart contract verified. So this will be it from me. I'll hand it back to Franklin.
Thank you. And I will finish with a few words about the current state of Linea and what we are having for the coming months. So for now, since January the 9th, we have been deploying Linea on the Gurley testnet. Since March the 28th, we have actually a public beta on the Gurley testnet. And since July the 11th, we actually have deployed Linea on the mainnet, where we are currently onboarding our partners, so that in the coming weeks, when everything will be ready, we will be targeting the communication more towards the end users and the other apps, so that when they come in, they will have a ready-to-use ecosystem with a lot of services that will already be available. So in the coming months or semesters, our main goals are first to finish implementing 100% coverage of the EVM, then work on the open sourcing of the whole software pieces of Linea. For now, only the smart contract has been audited and published on a free license, and we intend to do the same thing for the other pieces that Olivier just presented. Finally, on a slightly larger time frame, we are working towards decentralization of Linea, which means welcoming privately owned sequencers and provers onto the Linea L2. And here are a few links that may be of interest, and if you have any questions, you are more than welcome. Thank you.
Yeah, someone has any questions? Okay, sounds good. Thank you.